Here's a video about it's a particular example of a cool mapping of the plane to the plane, and particularly focusing on how to use the matrix of derivatives for a mapping like this. But first, we want to analyze the picture of the mapping. So here's the formula for the mapping. T of uv is u squared minus v squared for x and 2uv for y. And I'd like to get some sort of picture of that. And in fact, there's a beautiful picture sort of a little bit secretly underneath this, but let's just kind of approach it without a lot of sophistication first. So I'm going to go through this problem that I've laid out step by step. So for example, the first thing you could do is draw the image of just certain parts of the UV plane. When we do change of variables for integrals, for example, we're more interested in regions, and we're actually more interested in taking stuff in the target and bringing it back, as I've talked about already. But here, let's just analyze the transformation by taking stuff here and taking it over here. Well, so we could do points or segments, but let's do some rays. The positive v-axis. Okay, I'll just label that. That's piece A, and we're going to produce an output curve. There's the input curve. Let me put a little arrow on it. Let's say if we go along this curve in this way, and then we track the images under this mapping of all those points, where does that show up? Okay, well, those are all the points of the form 0, comma v. We could use t here if we wanted to emphasize that we just kind of set a bug to walking along here. But we can use v because the letter's perfectly appropriate to use. So we put all the points of 0, v, and we put them into this transformation. Oh, I'm using t. I changed my mind. Okay. All right, so I just plug that into the formula up here, and I'm going to get minus v squared 0. Okay, so that's, now remember, it's very important to realize there's not going to be a parabola here, just because this is squared. I just want to look at what all those things are. Where's the image of that parametrized curve? I've just got a curve in the xy plane parameterized by a parameter that happens to be called v, and it's all the things of the form minus v squared 0. Well, that's basically any negative number, comma 0, or any non-positive number. So it's going to end up on the negative x-axis. And it looks like 0, 0 is going to be here, right, going to plot to itself. 1, 0 is going to be or say 0, 1 is going to go to minus 1, 0. And so the arrow is going to go this way. Okay, so this is a pretty good way to start getting an idea of the transformation. This piece goes to here. This direction goes to this direction. Okay, so what about repeating that for all the different half axes? Okay, so t of minus 0 minus v. We plug that into our formula up here, and we just get, again, minus v squared, because the minus squares away, 0. Oh, that's interesting. So if this is set B, looks like it's plotting also to the same thing. So already we're seeing it's not one-to-one. And the abbreviation for that is 1-1. It's not one-to-one. Interesting. And so, and it looks like if I start at the origin, 0, 0 will go to 0, 0. And as I go out, this will go out. So this is really both A and B, the images. Okay. What about the x-axis? T, or the u-axis. Anything of the form u0 goes to u squared, comma 0. That's interesting. I'm never getting anything in v. That's kind of boring so far. We'll see that come out soon. Okay, so if this is c, as I go out from the origin here, this just goes out like this. And I'll just scooch it in here. What about the negative u-axis? That's, well, the same thing. Okay, so c and d, if we call this d. So it's folding things over, and so far I haven't gotten anything except on the axis. Of course, I'm going to be able to get something off the axis, and that's going to be crucial to have either u or v non-zero. So that's what c is about here. What if I look at the line u equals v? Call that piece E. I want to know what it does over here. So that's anything of the form u. Ah, now it's getting interesting. Ah, u squared minus u squared, now that's 0. And I get 2u squared. Well, that's interesting. So that's going to be everything where the x is 0 and this is a non-negative number. So it's not going to give the whole y-axis, it's going to give just this piece. So all of this is going to show up here. Now, it's a little tricky. As I go out from the origin and I go this way, it's not hard to see that I'll go this way. But if I go out from the origin down here, if these are negative, I still get these positive numbers here when I square it. So in fact, the outward directions both map to this arrow here. So this whole thing does get folded on itself. And so this whole line goes over to here. Okay. And then one more. F t of u minus u. That's how you can parameterize the line where u equals minus v. That's still going to be 0 because u squared minus the quantity minus u squared is 0. And then this is going to be minus 2u squared. Aha, that's where we finally get the negative axis. Same deal, going outward from the origin in either direction goes outward in here. That's funky. So it's definitely a lot of folding, a lot of 2 to 1-ness, seemingly. It's kind of a conjecture here. We're getting a lot of things where 2 points get mapped to the same point. Maybe there's more than 2 to 1-ness, but maybe there's many points going to the same point. But in fact, it really is going to turn out to be 2 to 1-ness. We'll see that in a minute. Okay. So, part D. Here I ask, we've got these straight lines mapping to straight lines, or at least rays. Okay. Are they mapped with or without stretching or shrinking? Well, that's where these squares come in. Okay. So, for example, this guy. The square didn't matter except that it was just any positive number. But now here's where it matters. If I go out from like 0, 0 to 1, 1 to 2, 2, let's take a look at where those points go. They go 0, 0, and then 0, comma 2, and then 2, 2 goes to 0, comma 8. Whoa, that's way up here. Okay. And then 3, 3 would go to 0, 18. Ooh, that's going to get way stretched off the top. And so, in fact, that's telling us that there is going to be a non-uniform stretching, or maybe shrinking. In fact, a shrinking will occur, I claim, when you have small numbers. Like if you take 1/2, 1/2, it shows up at like a half. If you take a half, it's going to show up much smaller. So it turns out that there's both stretching and shrinking. The main thing is that there's this non-uniform stretching and shrinking. So it's not just enough to really understand a map. It's not really enough to say these lines go to these rays. It does matter that there's some stretching and shrinking going on. Okay. So this is definitely not yet a complete picture of this map. We don't know what hits these quadrants, for example. The only possible outputs have been these rays. But we've got some idea that it has something to do with sort of folding over stuff and doubling, sort of double covering stuff. Okay. Now what about E here? Is the image of line y equals 1 a straight line, or v equals 1? Let's see. Let's, well, I can put it on the same picture still. It's not getting quite too busy. So u equals 1 is like this. Okay, so we're going to take anything of the form u equals 1, and v is anything. Okay, we're going to plug that in. That's 1 minus v squared and 2v. So if that were your parametrized curve, what does that look like? Now here's where a parabola comes in, because we can notice that v is y over 2, and x is then 1 minus y over 2 quantity squared. So it's where y is anything and x is a quadratic function of y. It's it got vertex where v equals 0, you get 0, 1. And then it's going leftward. It's a negative and it's a y squared. So it's something like this. That's definitely not a straight line. And we could draw lots more of those curves, and that would give us an even better idea of what the transformation is. But I don't want to take the time to do that. And you can actually even see that in like the Stewart textbook, for example. See a bit of a picture of that. The main thing is, I wanted to make sure that we see that there's a lot of these things that are not straight lines, definitely. V equals 1. That's going to be t of anything for u and 1 for v. That's u squared minus 1 and 2u. That's very, very similar. That's, again, going to be a parabola, because there's a quadratic relationship between the x, which is u squared minus 1, and y, which is 2u. Okay. So we've got the beginnings of a picture of the map, and it would be a lot of work to, by hand, generate a picture of that map. Let me make some comments, though, that aren't really directly related to the general topic here, but specific to this map. When I've got this map, there's a reason I picked this in particular, because I love this mapping. Most people love this mapping, you know about it. Because there's a very cool observation. If I think about complex numbers, I'm just going to mention this briefly. If I think about complex numbers, and if I square a complex number, then what do I get? I get u squared plus 2iuv plus iv quantity squared, which is u squared minus v squared, because the I squared becomes a minus 1, plus I times 2uv. That's interesting. Look at that. So if I think of uv as a point in the plane, parameterizing a complex number, then this guy corresponds to just z squared, because there's the real part of z squared, and here's the imaginary part of z squared. So the simple description is, if you like complex algebra, is t of z is just z squared. That might not help us at all with the geometry, because complex squaring is not super trivial. It's not as simple as with real number squaring. But there is a wonderful fact about that, which is de Moivre's theorem, which basically says if you use polar form, then if z is r cis theta, remember that's cosine theta plus I sine theta, then z squared, there is a simple description there. The magnitude squares and the angle doubles. That means that, in fact, we were, in a way, kind of looking at almost the wrong things, especially when we said, like, u equals 1 or v equals 1. We were guaranteed to get complicated stuff there. If you look at it in polar form, if you look at, like, theta equals pi over 4, and r is anything, this will tell you, okay, then anything positive, let's say. Then the square of that, r squared is going to be anything positive, and the theta is going to be double that. Okay. So if we call that, like, what are we up to? Well, I'll start over. Piece A, then that goes to the axis here. If we look at, let's check one of the ones we had before. Call that piece B, the y-axis. That's where theta equals pi over 2. Double that, we get theta equals pi. Oh yeah, we found that before, that this guy ended up over here. Similarly, a circle, like the unit circle, r equals 1, is going to go to the unit circle. And the circle r equals 2 is going to go to a circle r equals 4. Okay, so if we call that like C and D, then this is C and D. So that leads to a much nicer description of this this function, but it's kind of special to this, that it works so nicely when you describe everything with polar. Okay, but I couldn't avoid mentioning that. Okay, so the next thing to do is to look at this and think about what does the matrix of derivatives mean for this. And that'll be in the next video.